Today's lesson, lesson 3.3, deals with measures of position. But before we get into the measures of position, I'd like to take a moment and look at something called the empirical rule. The empirical rule is one that applies only to the normal distribution. And the normal distribution is that bell-shaped curve that we looked at earlier, in which the mean, median, and mode were all the same value. Well, when we consider the measures of spread or measures of variation, the empirical rule states that we have, within one standard deviation, we have 68% of the data. Within 2 standard deviations of the mean, we have 95%. And within 3 standard deviations of the mean, we have 99.7. Well, to look at that a little better, what we have here is a bell-shaped curve, a normal distribution. And what the empirical rule is telling us is within this first standard deviation, right here from this point to this point, ooh, I'm shaking quite a bit, that this is 68% of the data fall within that one standard deviation of measure. Within 2 standard deviations, so if we go out another standard deviation, right here 2 to the right of the mean, and then 2 to the left of the mean, then that accounts for 95% of the data. And if we go out 3 standard deviations, then that brings us to here, and we have 99.7% of the data. Almost all the data is covered within that 3 standard deviations of the standard normal distribution. Now, we're going to use that fact that we know that these percentages lie within 1, 2, and 3 standard deviations. So moving on to section 3.3, we're going to look at the z-score, the percentile, the quartile, and outliers. So first of all, to begin with the z-score. The z-score, or otherwise known as standard score, is obtained by subtracting the mean from the value and dividing the result by the standard deviation. So basically what we have here is a rule. This is our rule right here. That z is equal to x minus the mean divided by the standard deviation. Well, what is a z-score? A z-score represents the number of standard deviations a value is above or below the mean. So as we go back and look at that normal distribution, this bell-shaped curve here, and we consider a z-score, let's see if I can find where my pen is. We're thinking about, for the standard normal curve, that the mean is 0. So here's the center of our distribution. And each standard deviation is 1 unit. So this distance is 1. So that means this measure is 1. This measure is 2. And this is 3. And this is no longer an x-axis, but it's a z-axis, because it goes with the standard normal curve. Also, when we move 1 standard deviation to the left, then this value is now a -1. And this value is a -2. And this one is a -3. Now, how are we going to use that? Well, let's look at a problem. Here we've got a student who scored a 65 on a calculus test that had a mean of 50. Now, can you imagine? The average score in the class was a 50. And a standard deviation of 10. She also scored a 30 on a history test. But look at this mean. It's 25, and the standard deviation is 5. So we want to compare her relative positions on the 2 tests. Well, if we think of, this normal distribution here, this normal curve, we have here, and for the calculus test, the mean is 65. I'm sorry, the mean is 50. Let me change that. Helps if I, okay. So the mean here is 50. The standard deviation is 10. That's in the first part. So this means this measure has got to be 60. This is 70. This is 80, because we're going out 10 units, 3 standard deviations to the right. And if we go 3 to the left, this is sitting here at 40, 30, 20. So her score of 65 would be located right here. She did better than half the class. Actually, she did better than 1 standard deviation above the mean. Well, in the other class, in her history class, the mean score was a 25. So that means this measure right here is 25. Let me choose a different color. Until I'm really trying to learn this technology stuff. 1 standard deviation to the right. This puts this at 30. This is 35. And 40. Because the standard deviation is 5 right here, that means this distance from the mean to the first standard deviation is 5 units. And we go in the opposite direction the same way. So here we have a score of 20, 5 to the left, 5 more to the left, 15, and 10. But her score on this test is sitting here at a 30. Now, she did better than the mean, that 25 that's here in the curve. But did she do better relative to her classmates in history or in calculus? Well, it appears that she did better in the calculus. But the way we determine that using that little formula for the z-score is this. We're going to take her calculus score. Her calculus score was a 65. Let's see what my thing is. Okay. Her calculus score was a 65, and we're going to subtract the mean, 50, and divide by 10. So it tells us she's located at 1.5 standard deviations above the mean. That's a positive. And her history score was a 30. We subtract the mean of 25 and divide by the standard deviation of 5, and that puts her at a 1.0 in history. So her position in the calculus class is higher. Now, if we go back to that slide we just had a moment ago, notice here that is what that looks like. When we have this would be at 1, so 60 is at 1, 65 is at 1.5, and here the 30 is at 1. But we did the calculation with the equation for the z-score. Now, another measure of position is percentiles. And percentiles just separates the data set into 100 equal groups, percent, 100. And what it's talking about when you look at a percentile rank is the percentage of data values that fall below that particular value, that datum. So as I'm looking at a percentile graph, and this is looks like an ogive with cumulative percentages, here. So, oops, good grief, what did I do? So let me see. Okay. So we're considering these percentages on the left-hand side, right here, and we have across the bottom the actual values, the class boundaries as they're listed. So for a percentile of 40, notice that it corresponds to something like 118 as a score. And for a percentile of 70, it corresponds to something like 132. Or you could look in reverse and say, well, if the score is 132, what percentage of values fall below that 132? That's going to be 70%, fall below that 132. Now, what we'll be using primarily for our class is quartiles. And quartiles separates the data set into 4 equal groups, quarters. Now, I know here on the slide it mentions the 25th percentile, the 75th percentile, but we're primarily focusing on quartile 1, quartile 2, quartile 3. And another little definition we need to add to our notes is this interquartile range. The interquartile range, like range is the difference in the min and the max. Well, the interquartile range is the difference in quartile 3 and quartile 1. So we're just going to subtract those two and get a single number for the interquartile range. To find the quartiles, these are our steps. We arrange the data in order from lowest to highest. Find the median. That is the value for, and we'll just call it median. They've named it as quartile 2. Step 3, then we want to find just the first half of the data set. The median for that is quartile 1. And then in step 4, the second half of the data set, the median for that is quartile 3. Well, let's look at an example. Here we've got a set of data. And for this set of data, we're looking for the quartile. We're looking quartile 1, 2, and 3. So to do that, the first thing we have to do is we have to put the data in order. And as you recall, when we do this, when we sort it in ascending order, to find the median, let's see if I can get there. To find the median, this value here, we separate the data into two separate parts. We have, this is the first half of our data set, and this is the second half. We got 4 values above, 4 values below. So our median has to be right here, between 13 and 15. So to find that value, we add 13 plus 15 divided by 2. That gives us 14. To find the first quartile, I'm not going to call this the median. I'm going to call this the quartile. I'm going to call this the median. To find the first quartile, we do the same thing. We're finding the median or the middle value for the first half of the data set. So that falls right here between the 6 and the 12. And so we add those together and divide by 2. So that's quartile 1. And then our third quartile is between 18 and 22. So we add those two together and divide by 2. So our third quartile is 20. Now, an outlier, when we consider quartiles, is an extremely high or low data value when compared to the rest of the data set. And there is a process by which we can use to find out if a value is an outlier or not. And the way we do that is we calculate quartile 1, subtract 1.5 times the IQR, and quartile 3 plus 1.5 times the IQR. In the next video, I'm going to show you a simpler way of finding an outlier in a set of data.